Welcome to Algebra 2. Today we've got section 6.4, transformations of exponential and logarithmic functions. So let's have a look. We've had these sections on transformations ever since chapter 1. I really like that consistency on the part of our textbook to constantly reinforce that idea of stretching and flipping and shifting graphs around the coordinate plane. That really helps us understand what a function should be doing graphically. So let's see how that pertains to these types of functions. All right, so what I've given you here, first of all, is showing all the different places we can multiply numbers in to an exponential, or add them in as well, to an exponential or a logarithmic equation. Now, I'm using the variables a, b, c, d, and e. Realize that e as a variable, I'm not talking about that 2.718 that we saw in section 6.2. It's just showing where we could add a number. So just to run through again quickly, a number out in front that is multiplied, if it's positive, it could be stretching or shrinking our graph. If it's a negative number, it will also apply a vertical flip to it. Then we've got b, which is just, in this case, the base of our exponential function. Then we have a multiplier on x, which, again, if it's positive, it could be stretching or shrinking our graph, controlling the how fast aspect of the graph, stretching or shrinking horizontally. If it's a negative, it could also flip that graph horizontally. Then we've got plus d. Notice that it's all in this exponent. The exponent is like the input area. That's where all the horizontal work happens. And this plus d, that could affect the shifting of the graph left and right. And then lastly, we have a place to add a number outside the function that would shift the graph either up or down. And going with it would be the horizontal asymptote on the exponential function. So we'll keep that in mind. For the logarithm, again, we've got the same multiplier out front. And again, that affects vertical flips or stretches or shrinks. Then b, again, that's just the base of the logarithm. That doesn't do anything transformation-wise. It just tells us what type of logarithm we're dealing with. We've got our horizontal flip, stretch, or shrink variable c. We've got our shift left and right variable d. Notice the input area of the logarithm is the argument, so that's where all the left and right adjustments happen. And then again, we have plus e on the outside, that last place. It could be adding or subtracting a number to raise the graph up or down. Right, to illustrate this, I've included this out of the textbook. It's just, I call it the transformation library, just giving you some examples of different types of adjustments made to exponentials and to logarithmic functions as well. So take those and use them as you will. Sometimes it's nice to have an example to look back to. But we've been doing this for a little while, so I think we should be pretty confident with it. And going right along with that, this should be a pretty quick lesson. All right, so how have we seen these transformations in the past? Well, the first thing is to look at the function and describe the transformation that is happening. So for number 16, we start off with a function that is 1/3 to the x. That's an exponential decay function. And they say g of x is 1/3 to the x plus 2 power, and then minus 2/3. So what's happening? I notice that in the input area, they're adding 2 to x. That is shifting the graph left 2 units. And then that minus 2/3 outside, well, that's shifting the graph down 2/3 units. All right, so if I were to graph number 16, I know that it's still an exponential decay function, but now its horizontal asymptote is not on the axis anymore. It's been shifted down a little bit, and that's how I would see that decay function graphed. All right, for number 28, here we've got a log base 1/3 of x, and then our transformation is log base 1/3 of negative x, and then plus 6. Well, I know that negative sign that's multiplied into the input, into x, that is causing a horizontal flip. And then the plus 6 that is outside that input area, outside the logarithm, that's causing it to shift up 6 units. So again, if I'm thinking of that graphically, typically a logarithm looks like that. Ours is going to be horizontally flipped and raised up 6 units. So we could expect it to look something like that. And just a very general idea of the shape, but knowing that just by looking at the function is a really, really powerful tool. Helps us out more than we appreciate. All right, so how can we extend this idea? Well, we kind of casually mentioned it in the last slide. We're still describing the transformation, but now we're going to state the equation of the asymptote. All right. So 46, I start off with this f of x equals 3 to the x, which I know has a horizontal asymptote y equals 0. That's our way of expressing the x-axis. G of x, what they're doing is they are subtracting 9 from the input, so it's shifted to the right 9 units. And then they subtract 2 outside that exponential term, so it's also shifting down 2 units. And since they've shifted that whole graph down, they've also shifted the horizontal asymptote down. So my horizontal asymptote on G, make that a colon instead, is y equals -2. All right, so really nice relationship with that number outside and our horizontal asymptote for exponential functions. We're always looking for patterns. That is definitely one we want to see if it holds true when we go through our homework. Number 48, here we've got a log base 1/5 of x, which I know that logarithms have vertical asymptotes, and I can find those by looking at the argument. What would make that argument 0? Well, if x equaled 0, that would zero out the argument, so that's my vertical asymptote. Well, what are they doing in our function, though? They're taking the graph and shifting it 1 unit to the right, and then also up 13 units. All right, well, a logarithm has a vertical asymptote, so now I'm concerned with how the shifting is happening left and right. That's what would move that vertical asymptote. The up and down has no effect on logarithms. So my new vertical asymptote is the line x equals +1. Because of that 1 unit shift to the right, you can see my vertical asymptote. Now, what would it take to zero out that argument? If x were equal to 1, it would zero out the argument. That's my new asymptote. Okay, and knowing where the asymptotes are located really helps us draw our graphs, because we know that the graph will be pulled towards that line as we move along the curve. All right, next objective was actually constructing a function that is made by transforming another. Remember these followed by problems, I'm sure. Number 38, we start off with e to the -x. Then we shift it 4 units to the right and 1 unit down. And then we vertically shrink the result by a factor of 1/3. Okay, well, it's followed by, so I'm going to use this little placeholder h of x. I know I want to end up with g, but I've got to do one transformation, then another. So h of x is going to be 4 units right. So I'm going to take my function f, and I'm going to adjust the input by subtracting 4. That will shift it 4 units to the right. And then I will subtract 1 outside of the function. That will drop it down 1 unit. So what does that turn into? Well, I start off with e to the -x. So now I've got e to the negative x minus 4. The negative sign stays out front. I'm just swapping out the x with the quantity x minus 4, and then I subtract 1 afterwards. All right, and then I follow that up with a vertical shrink, and that's what leads me to g of x. So I take 1/3 outside times h of x, and in this case that means 1/3 times e to the negative quantity x minus 4 minus 1, and that 1/3 applies to all of it. Applies to all of it. Now, I'm sure we could simplify by distributing and simplifying some terms along the way, but I prefer your answers in this format right here so I can see where you are applying the numbers. You can always simplify later. Number 42, here we start off with a natural log of x function, 3 units right and 1 unit up. And then comes our followed by. So let's do that translating first. So h of x means I'm taking my function f, going 3 units to the right, so I'm adjusting the input by subtracting 3 from it. And then outside, I'm going to add 1 to lift it up 1 unit. Okay, and what that turns into when I actually look at what function f of x means, I'm going to have the natural log of x minus 3, and then plus 1 outside the logarithm. And then we want a horizontal stretch. Horizontal stretch. This is something that we have really been having a tough time with, horizontal stretches and shrinks. If a graph is stretched horizontally, it means it's taking a lot longer to cover that x-axis. So I'm thinking it's going 1/8 as fast. All right, so that means my function g of x is going to be h, but at 1/8 speed. So my input becomes 1/8 x instead of just x. All right, and what does that result in? The natural log of not x minus 3, but 1/8 x minus 3, and then our plus 1. So here we adjusted the input from x to 1/8 x, and that's it. That's how we deal with the horizontal stretch. It's taking so much longer left to right. Okay, and looking at this slide, it looks like this was just a leftover copy and paste from the previous section, so please disregard this slide. It was left in erroneously. Your assignment for section 6.4 on these transformations, yes, there are a lot of problems. 3 through 6 all, that's a matching section, so is 31 through 34. But for all of the odd problems, 7 through 29 and 35 through 47, we are skipping 43. It says to graph, do not graph them. I just want you to list off those different transformations. We want to be automatic with that. That does it for section 6.4 here in Algebra 2.